When we talk about a cone, the first associations that come to mind are ice cream cones and birthday caps. Now, let us look at a cone from the mathematical point of view. Consider a fixed vertical line L. Now, consider another line M that intersects line L at a fixed point V. Let the angle at which line M is inclined to line L be alpha. If line M rotates about point V such that angle alpha remains constant, it generates a double cone as shown. Such a cone is called a double right circular hollow cone. In this module, we will refer to this solid figure simply as a cone. Let us identify the different parts of a cone. The fixed vertical line passing through the center of the cone is called its axis. The rotating line M that generates the surface of the cone is called the generator. The fixed point at which the generator cuts the axis is called the vertex of the cone. The cone is divided into two parts by the vertex. The upper part is called the upper nape, and the lower one is called the lower nape. When a plane intersects a cone, it cuts a section from the cone. This section is called a conic section or a conic. We get different kinds of conic sections of different shapes depending on the position of the intersecting plane with respect to the cone and the angle it makes with the vertical axis of the cone. Consider a plane that intersects a cone at any position other than the vertex and makes an angle beta with the axis of the cone. Now, we have several possibilities. If the plane intersects one nape of the cone at right angle to the vertical axis, the resulting conic section is a circle. If the plane intersects one nape of the cone such that angle beta is greater than angle alpha, but less than 90 degrees, the resulting conic section is an ellipse. If the plane intersects one nape of the cone such that angle beta is equal to angle alpha, the resulting conic section is a parabola. If the plane intersects the cone such that angle beta is less than angle alpha and greater than or equal to 0, the plane cuts across both napes of the cone, and the resulting conic section is a hyperbola. Observe that in the formation of conic sections in the form of a circle, ellipse, or parabola, the plane intersects only one nape of the cone. However, in the formation of a conic section in the form of a hyperbola, the plane intersects both the napes of the cone. Also note that in the formation of these conic sections, the intersecting plane does not pass through the vertex of the cone. Conic sections have a large number of practical applications. Historically, the circle has provided momentum to our economic and industrial development. The ellipse is used extensively for studying planetary motion and making advanced reflectors for automobile headlights. Parabolas are used to study the trajectories of projectiles. Hyperbolas are used to study sonic booms created by supersonic aircraft and to study the propagation of waves and movement of subatomic particles. Thus, the study of these conic sections finds many practical applications in different branches of science. You have seen that when a plane intersects the nape of a cone at any place other than the vertex, such that the angle between the plane and the axis of the cone is 90 degrees, the section of the cone is a circle. Let us recall the definition of a circle. A circle is the set of all the points in a plane that are equidistant from a fixed point. The fixed point is called the center of the circle. The distance between any point on the circle and the center is called the radius of the circle. A circle can have an infinite number of radii, and all its radii are equal. Now, let us derive the equation representing a circle on a coordinate plane. Let point P with the coordinates h and k be the center of a circle. Consider a point M on the circle. Now, by definition, distance PM is equal to the radius of the circle. Recall the distance formula used to find the distance between 2 points whose coordinates are known. Applying the distance formula, we find an expression for the radius of the circle in terms of the coordinates of its center, P, and a point M on it. Squaring both sides, we get the equation representing a circle in a coordinate plane. In this expression, h and k represent the coordinates of the center of the circle and r represents its radius. Now, let us consider a circle whose center lies at the origin. In this case, both the coordinates of the center of the circle will be 0. Putting the values of h and k as 0 in the equation of the circle, we get the equation representing a circle with its center at origin and radius r. This is the simplest form of the equation of a circle. Let us find the equation of the circle with the center at the point 3, 2 and radius 3 units. Here, the x-coordinate of the center, or h, is equal to 3. The y-coordinate of center, or k, is equal to 2, and the radius r is equal to 3. Putting in the values of h, k, and r, we find the equation of the given circle. Let us simplify the equation further. Let us open the brackets and rearrange the terms. Thus, we get the final equation of the given circle as x square plus y square minus 6x minus 4y plus 4 is equal to 0. Both the equations shown here represent the same circle. Now, let us further rearrange the terms in equation 2. This gives another form of the equation of a circle, called the general equation of the circle. Note that minus g and minus f represent the coordinates of the center of the circle, and c represents the constant term in the equation. Thus, in the general equation of a circle, the coordinates of the center are given by minus g and minus f. In the general equation of a circle, the radius is given by the square root of g square plus f square minus c. Note that every equation of the form x square plus y square plus 2gx plus 2fy plus c is equal to 0 represents a circle only if the value of g square plus f square minus c is greater than or equal to 0. If the value of g square plus f square minus c is 0, then the equation of this form represents a point circle, which is nothing more than just a point or the center of a circle. If the value of g square plus f square minus c is less than 0, then The equation of this form represents an imaginary circle with a real center. You know that when a plane intersects one nape of a cone at any place other than the vertex, such that angle beta between the plane and the axis of the cone is equal to angle alpha between the axis and the generator of the cone. The resulting conic section is a parabola. If you throw a solid object in the air at an angle to the ground, the trajectory of the object is a parabola. Consider a fixed straight line L in a plane. Also consider a fixed point F in the same plane but not on line L. Now consider points P1, P2 and P3 such that their distances from the fixed line L and the fixed point F are the same. Then the curve passing through all such points is a parabola. Thus, a parabola is the set of all the points in a plane that are equidistant from a fixed line and a fixed point in the plane. Remember that the curve of a parabola forms only if the fixed point F does not lie on the fixed line L. If point F lies on line L, then the parabola becomes a straight line. This is also called the degenerate case of a parabola, explained earlier. The fixed point F in the plane is called the focus of the parabola. The fixed line L in the plane is called the directrix of the parabola. The line passing through the focus and perpendicular to the directrix is called the axis of the parabola. A parabola is symmetrical about its axis. Thus, the axis of a parabola is also called its axis of symmetry. The point where the axis intersects the curve of a parabola is called the vertex of the parabola. The line segment passing through the focus, perpendicular to the axis and with its endpoints on the curve of the parabola, is called the latus rectum of the parabola. If we consider a parabola with its vertex at the origin and its axis along the x or y axis, then there are four distinct possibilities. We can have the axis of symmetry of the parabola along the x-axis with the focus of the parabola on its positive side and the directrix cutting the negative side. Here, note that since vertex O is also a point on the parabola, its distance from the focus and the directrix will be the same. Thus, if the axis of symmetry lies along the x-axis, the vertex lies at the origin and the focus at A, 0, then the directrix will intersect the x-axis at -A, 0. As another possibility, we can have the axis of symmetry along the x-axis with the focus of the parabola on its negative side and the directrix cutting the positive side. We can also have the axis of symmetry along the y-axis with the focus of the parabola on its positive side and the directrix cutting the negative side of the y-axis. Or we can have the axis of symmetry along the y-axis, the focus of the parabola on its negative side and the directrix cutting the positive side. Let us derive the equation of the parabola for case 1 with the axis of symmetry along the x-axis, the vertex at the origin, the focus at A, 0, and directrix intersecting the x-axis at -A, 0. Consider a point P on the parabola with the coordinates x, y. Join P to F. PF is the distance of point P from the focus of the parabola. Let PB be the perpendicular drawn from point P on the directrix. Thus, PB is the distance from point P to the directrix. Since point B lies on the directrix, its x-coordinate will be -a. The y-coordinate of point B will be the same as that of point P, that is, y. We already know the formula for calculating the distance between two given points. Substituting the coordinates of points P and F in the distance formula, we get distance PF is equal to under root x minus a whole square plus y square. Let this be equation 1. Similarly, substituting the coordinates of points P and B in the distance formula, we get distance PB is equal to under root x plus a whole square. Let this be equation 2. By the definition of a parabola, distance PF is equal to distance PB. Equating the values of PF and PB from equations 1 and 2 and simplifying, we get y square is equal to 4ax. The equation y square is equal to 4ax represents the given parabola. Let us see if the coordinates of P as derived from the previous equation satisfy the geometrical condition stated in equation 1. Substituting the value of y square as 4ax in equation 1, we get PF is equal to PB. Thus, the geometrical condition is satisfied. Thus, the equation y square is equal to 4ax represents the parabola with the axis of symmetry along the x-axis, the vertex at the origin, the focus at a, 0, and directrix x is equal to -a. By similar derivation, the equation of the parabola with the axis of symmetry along the x-axis, the vertex at the origin, the focus at -a, 0, and directrix x is equal to a, is y square is equal to -4ax. The equation of the parabola with the axis of symmetry along the y-axis, the vertex at the origin, the focus at 0, a, and directrix y is equal to -a, is x square is equal to 4ay. And the equation of the parabola with the axis of symmetry along the y-axis, the vertex at origin, the focus at 0, -a, and directrix y is equal to a, is x square is equal to -4ay. These four equations are called the standard equations of a parabola. Here, we can make some interesting observations. Note that if the equation of the parabola has the term y square, then its axis of symmetry lies along the x-axis. If the equation of the parabola has the term x square, then its axis of symmetry lies along the y-axis. Also note that if the axis of symmetry lies along the x-axis, then the curve of the parabola opens to the right if the focus lies on the positive side of the x-axis, and the curve of the parabola opens to the left if the focus lies on the negative side of the x-axis. Similarly, observe that if the axis of symmetry lies along the y-axis, the curve of the parabola opens upwards if the focus lies on the positive side of the y-axis, and the curve of the parabola opens downwards if the focus lies on the negative side of the y-axis. Now, let us find the length of the latus rectum of a parabola. Consider a parabola with latus rectum AB. Let the distance OF between the vertex and the focus of the parabola be A. Since the distance of the focus and directrix from the vertex is the same in a parabola, we have distance FM is equal to 2A. Let us draw a perpendicular AC from point A to the directrix. Now, the distance AC is equal to FM. Thus, the distance of point A from the directrix is 2A. Since point A lies on the parabola, its distance from the focus F and the directrix must be the same. This implies that AC is equal to AF, or AF is equal to 2A. Since a parabola is symmetrical about its axis, distance FB is equal to distance AF, which is equal to 2A. Thus, the length of the latus rectum AB is equal to 4A, where A is the distance between the focus and the vertex of the parabola. You have seen that when a plane intersects the nape of a cone at any point other than the vertex, such that the angle beta between the plane and the axis of the cone is greater than angle alpha between the axis and the generator of the cone, but less than 90 degrees. The resulting conic section is an ellipse. We better know an ellipse as an oval shape. Now, let us recall the formal definition of an ellipse. Consider two fixed points, F1 and F2 in a plane. Now consider points P1, P2 and P3 such that the sum of their distances from F1 and F2 is equal. Then, the closed curve passing through all such points is an ellipse. Thus, an ellipse is the set of all those points in a plane, the sum of whose distances from two fixed points is constant. Remember that an ellipse is formed only by those points whose sum of distances from two fixed points is constant and greater than the distance between the two fixed points. The fixed points in the plane are the two focus points of an ellipse, jointly called the foci. The line segment passing through the foci of an ellipse and touching its sides is called the major axis of the ellipse. The 2 points where the major axis touches the ellipse are called the vertices of the ellipse. The midpoint of the major axis, or the midpoint of the line segment joining the foci of an ellipse, is called the center of the ellipse. The line segment passing through the center of an ellipse and perpendicular to the major axis is called the minor axis of the ellipse. A line segment joining the center of an ellipse to either of its vertices is called a semi-major axis. Clearly, a semi-major axis is half of the major axis of an ellipse. Similarly, a line segment joining the center of an ellipse to either of the endpoints of its minor axis is called a semi-minor axis. Clearly, a semi-minor axis is half of the minor axis of an ellipse. If the length of the major axis of an ellipse is 2a, the length of each of its semi-major axes is a. Similarly, If the length of the minor axis of an ellipse is 2b, then the length of each of its semi-minor axes is b. Also, if the distance between the two foci of an ellipse is 2c, the distance of either focus from the center of the ellipse is c. Let us now derive a relationship between length a of the semi-major axis, length b of the semi-minor axis, and distance c of a focus of an ellipse from its center. Consider a point P at one of the endpoints of the major axis of an ellipse. The distance of point P from focus F1 is equal to the distance F1 O plus OP. Since F1O is equal to C and OP is equal to semi-major axis A, PF1 is equal to C plus A. Also, the distance of point P from focus F2 is equal to distance OP minus distance OF2. Since OP is equal to A and OF1 is equal to C, PF2 is equal to A minus C. Thus, the sum of the distances of point P from foci F1 and F2 is equal to 2A. Let this be equation 1. Now, consider a point Q at one of the endpoints of the minor axis of the ellipse. The distance of point Q from foci F1 and F2 is given by QF1 and QF2. In right-angled triangle QOF1, hypotenuse QF1 square is equal to QO square plus OF1 square. Since QO is equal to semi-minor axis B and OF1 is equal to C, we get QF1 is equal to under root B square plus C square. Similarly, from right-angled triangle QOF2, we get QF2 is equal to under root B square plus C square. Thus, the sum of the distances of point Q from foci F1 and F2 is equal to 2 into under root B square plus C square. Let this be equation 2. Since both points P and Q lie on the same ellipse, by definition, the sum of their distances from foci F1 and F2 must be the same. Substituting the values of PF1 plus PF2 and QF1 plus QF2 from equations 1 and 2, we get 2A is equal to 2 into under root B square plus C square. On simplifying, we get C is equal to under root A square minus B square. Equation 3 gives an important relation between distance C of a focus of an ellipse from its center and its semi-major axis A and semi-minor axis B, and helps to understand some special cases of an ellipse. If distance C of a focus of an ellipse from its center becomes 0, then the two foci overlap each other. Substituting the value of C as 0 in equation 3, we get A is equal to B. Thus, if C is equal to 0, the lengths of the semi-major axis and the semi-minor axis of an ellipse become equal, and the ellipse becomes a circle with its foci as the center. If distance C of a focus of an ellipse from its center becomes equal to its semi-major axis, then the two foci become its vertices. Substituting the value of C as A in equation 3, we get B is equal to 0, Thus, if C is equal to A, the length of the semi-minor axis of an ellipse becomes 0, and the ellipse becomes a straight line. You already know that an ellipse is the set of all the points in a plane, the sum of whose distances from two fixed points is constant. You have also learnt about the various parts of an ellipse, like its two foci, two vertices, center, major axis, and minor axis. You also derived the relationship C square is equal to A square minus B square, where C is the distance of a focus from the center, A is the length of the semi-major axis, and B is the length of the semi-minor axis of an ellipse. Now let us look at another important relationship in an ellipse. Let K be the constant equal to the sum of the distances of any point on the ellipse from its foci. Since vertex A lies on the ellipse, the sum of distances AF1 and AF2 is also equal to K. Let this be equation 1. Now, AF1 is equal to AO minus F10, or the length of the semi-major axis A minus distance C of focus F1 from the center. AF2 is equal to AO plus OF2, or the length of the semi-major axis A plus distance C of the focus F2 from the center. Substituting the values of AF1 and AF2 in equation 1, we get K is equal to 2A. What is true for vertex A is true for all the points lying on the ellipse. Thus, the sum of the distances of any point on an ellipse from its foci is equal to the length of the major axis, or 2 times the semi-major axis of the ellipse. Eccentricity is another important concept associated with all conic sections. It is a measure of the deviation of a conic section from being a circle. The eccentricity of an ellipse is denoted by E and is equal to the ratio of the distance of a focus from the center to the length of the semi-major axis of the ellipse. Squaring both the sides of the formula for eccentricity and simplifying, we get B square is equal to A square into 1 minus E square. Remember this formula as it comes handy in solving many problems. Let us now derive some standard equations that are satisfied by all the points lying on an ellipse. If we consider an ellipse with its vertex at the origin and its major axis along the x or the y axis, then there are 2 distinct possibilities. The first possibility is that an ellipse has its center at the origin and its major axis along the x-axis. In this case, the foci of the ellipse lie on the x-axis. The second possibility is that an ellipse has its center lying at the origin and its major axis along the y-axis. In this case, the foci of the ellipse lies on the y-axis. Let us derive an equation of the ellipse for case 1 with its center at the origin, the major axis along the x-axis and the foci at minus c, 0 and c, 0 on the x-axis. Consider a point P on the ellipse with the coordinates x, y. The sum of the distances PF1 and PF2 is equal to 2a. Let this be equation 1. We already know the formula for calculating distance between two given points. Using the distance formula, we get distance PF1 is equal to under root x plus c whole square plus y square. Similarly, using the distance formula, we get distance PF2 is equal to under root x minus c whole square plus y square. Let us substitute the values of PF1 and PF2 from equations 2 and 3 in equation 1. Rearrange the equation. Square both the sides of the equation. On simplifying, we get under root x minus c whole square plus y square is equal to a minus c upon a x. Squaring both the sides again and simplifying further, we get equation 4. Substituting the values of a square minus c square as b square in equation 4 and simplifying further, we get x squared upon a square plus y square upon b square is equal to 1. We can say that equation 5 represents the given ellipse if the coordinates of point P as derived from this equation satisfy the geometrical condition PF1 plus PF2 is equal to 2a. From equation 5, we get y square is equal to b square into 1 minus x square upon a square. Substituting the value of y square from equation 5 in equation 2 and simplifying, we get PF1 is equal to a plus c upon a into x. Substituting the value of y square from equation 5 in equation 3 and simplifying, we get PF2 is equal to a minus c upon ax. Substituting these values of PF1 and PF2 in equation 1, we see that the geometric condition is true. Thus we can say that point P lies on the ellipse represented by equation 5. The equation x squared upon a square plus y squared upon b square is equal to 1 is the standard equation for an ellipse with its center lying at the origin and the major axis lying along the x-axis. Similarly, we can derive the standard equation for an ellipse with its center at the origin and the major axis along the y-axis as x squared upon b square plus y squared upon a square is equal to 1. These two equations are called the standard equations of an ellipse having its center at the origin and the major axis along the x or the y-axis. Here, we can make some interesting observations. In an ellipse, the length of the major axis is always greater than the length of the minor axis. Thus we can say that if the denominator of the x squared term is greater than the denominator of the y squared term, then the major axis of the ellipse lies along the x-axis. Similarly, if the denominator of the y squared term is greater than the denominator of the x squared term, then the major axis of the ellipse lies along the y-axis. Note that both the standard equations of an ellipse contain even paths of x and y. Therefore, an ellipse with its center at the origin and the major axis along either the x or y-axis is symmetrical about both the coordinate axes. What this means is that if a point px, y lies on the ellipse, then the points minus x, y, x, minus y, and minus x, minus y also lie on the ellipse. A line segment passing through the focus and perpendicular to the major axis with its endpoints lying on the curve of an ellipse is called the lattice rectum of the ellipse. Since an ellipse has two foci, it has two lattice recta. Lattice recta is the plural for lattice rectum. Consider an ellipse with its center at the origin and the major axis along the x-axis and lattice recta AB and CD. Let the length AF2 be L. If C is the distance of focus F2 from center O, the coordinates of point A are C, L. Recall the standard equation of the ellipse with its center at the origin and the major axis along the x-axis. Since point A lies on the ellipse, its coordinates must satisfy the standard equation of the ellipse. Substituting the coordinates of point A in the standard equation of the ellipse and simplifying, we get L is equal to b squared upon A. Since the ellipse is symmetrical about the x-axis, distance AF2 is equal to distance F2b. Hence, the total distance AB is equal to 2b squared upon A. Distance AB is the length of the lattice rectum. Thus, the lattice rectum of an ellipse with the semi-major axis equal to A and the semi-minor axis equal to B is given by 2b squared upon A. You know that when a plane intersects a cone at any place other than the vertex, such that the angle beta between the plane and the axis of the cone is less than the angle alpha between the axis and the generator of the cone, and more than or equal to 0 degrees, and the plane intersects both the napes of the cone, the resulting conic section is a hyperbola. Notice that a hyperbola is made of two curves that appear like mirror images of each other. Consider two fixed points F1 and F2 in a plane. Now, consider points P1, P2 and P3, such that the difference of their distances from F1 and F2 is equal. Then, the curves passing through all such points form a hyperbola. Thus, a hyperbola is the set of all the points in a plane, the difference of whose distances from two fixed points in the plane is constant. Remember that to find the difference between the distances of a point from the fixed points F1 and F2, we always subtract the distance of the nearer fixed point from the distance of the farther fixed point. The fixed points in the plane are the two foci of a hyperbola. They are jointly called the foci of the hyperbola. The line passing through the foci is called the transverse axis of the hyperbola. The 2 points where the transverse axis intersects the curves of a hyperbola are called the vertices of the hyperbola. The midpoint of the line segment joining the foci is called the center of the hyperbola. The line passing through the center and perpendicular to the transverse axis is called the conjugate axis of the hyperbola. The distance between the two vertices of a hyperbola is considered the length of its transverse axis. Thus, if A and B are the two vertices and distance AB is 2a, then the distance of either of the vertices from the center of the hyperbola is a. The center bisects the transverse axis into two semi-transverse axes. Also, if the distance between the two foci is 2c, the distance of either foci from the center of the hyperbola is c. Now, here is something just for your understanding. The intersecting blue lines that you see passing through the center of the hyperbola are called its asymptotes. An asymptote is a tangent to the hyperbola at infinity. If you draw a tangent to the hyperbola through any of its vertices, the tangent intersects the symptotes as shown. Draw perpendiculars on the conjugate axis from the points where the tangent intersects the asymptotes. The distance between the 2 points where these perpendiculars meet the conjugate axis is considered the length of the conjugate axis of the hyperbola. You just have to remember that the length of the conjugate axis of a hyperbola is represented by 2b and gets bisected by the center. The center bisects the conjugate axis into two semi-conjugate axes. Now, we can state an important relationship between lengths A, B and C. If the lengths of the semi-transverse and semi-conjugate axes of a hyperbola are equal to A and B respectively, and the distance between its foci is 2c, then b squared is equal to c square minus a square. Now, let us find the difference of the distances of a point on a hyperbola from its foci. Let P1, P2 and P3 be any 3 points on the hyperbola. By definition, we know that the difference between the distances of a point on a hyperbola from its foci is constant. Let this constant be k. Consider vertex A that lies on the hyperbola. The difference in the distance of point A from the two foci is given by AF2 minus AF1. Since AF2 is equal to AB plus BF2, we get K is equal to AB plus BF2 minus AF1. Let this be equation 1. Now, consider the other vertex B that lies on the hyperbola. The difference in the distance of point B from the two foci is given by BF1 minus BF2. Since BF1 is equal to AB plus AF1, we get K is equal to AB plus AF1 minus BF2. Let this be equation 2. Equating the values of K from equations 1 and 2 and simplifying, we get BF2 is equal to AF1. Substituting the value of AB as 2a and BF2 as AF1 in equation 1, we get the value of K as 2a. Similarly, from equation 2, we get the value of K as 2a. This is true for all the points on a hyperbola. The difference between the distances of any point on a hyperbola from its foci is equal to the length of the transverse axis of the hyperbola. We have already seen that a hyperbola is the set of all that points in a plane such that the difference of their distances from two fixed points in the plane is constant. You have also learned about the parts of a hyperbola, like its two foci, two vertices, center, transverse axis, and conjugate axis. We also derived the relationship b square is equal to c square minus a square, where c is the distance of a focus from the center, a is the length of the semi-transverse axis, and b is the length of the semi-conjugate axis of a hyperbola. We also observed that the difference between the distances of any point on a hyperbola from its foci is equal to the length of the transverse axis of the hyperbola. Eccentricity is an important concept associated with all conic sections, including a hyperbola. It is a measure of the deviation of a conic section from being a circle. The eccentricity of a hyperbola is denoted by E and is equal to the ratio of the distance of a focus from its center and the length of its semi-transverse axis. From the expression for eccentricity, we get C is equal to EA. Thus, the distance of a focus from the center of a hyperbola is equal to the product of its eccentricity and the length of its semi-transverse axis. If we consider a hyperbola with its center at the origin and its transverse axis along the x or the y axis, then there are two distinct possibilities. In the first case, we can have a hyperbola with its center lying on the origin and its transverse axis along the x-axis. In this case, the foci of the hyperbola lie on the x-axis. In the second case, we can have a hyperbola with its center lying on the origin and its transverse axis along the y-axis. In this case, the foci of the hyperbola lie on the y-axis. Let us derive the equation of the hyperbola for case 1 with the center at the origin, the transverse axis along the x-axis, and the foci lying at minus c, 0 and c, 0 on the x-axis. Consider a point P on the hyperbola with the coordinates x, y. Then, by definition, the difference of the distances PF1 and PF2 is constant and equal to 2a. Let this be equation 1. We already know the formula for calculating the distance between two given points. Using the distance formula, we get distance PF1 is equal to under root x plus c whole square plus y square. Let this be equation 2. Similarly, using the distance formula, we get distance PF2 is equal to under root x minus c whole square plus y square. Let this be equation 3. Let us substitute the values of PF1 and PF2 from equations 2 and 3 in equation 1. Rearrange the equation. Square both sides of the equation. On simplifying, we get under root x minus c whole square plus y square is equal to c upon a into x minus a. Squaring both sides again and simplifying further, we get equation 4. Substituting the value of a square minus c square as minus b square in equation 4 and simplifying further, we get x squared upon a square minus y squared upon b square is equal to 1. We can say that equation 5 represents the given hyperbola if the coordinates of point P as derived from this equation satisfy the geometrical condition PF1 minus PF2 is equal to 2a. From equation 5, we get y square is equal to b square into x square upon a square minus 1. Substituting the value of y square from equation 5 in equation 2 and simplifying, we get PF1 is equal to a plus c upon a into x. Substituting the value of y square from equation 5 in equation 3 and simplifying, we get PF2 is equal to c upon a into x minus a. Substituting these values of PF1 and PF2 in equation 1, we see that the geometric condition is true. Thus, we can say that point P lies on the hyperbola represented by equation 5. The equation x square upon a square minus y square upon b square is equal to 1 is the standard equation for a hyperbola with its center at the origin and the transverse axis lying along the x-axis. Similarly, we can derive the standard equation for a hyperbola with its center at the origin and the transverse axis along the y-axis. The equation is y squared upon a square minus x squared upon b square is equal to 1. These two equations are called the standard equations of a hyperbola having its center at the origin and the transverse axis along the x or y-axis. Here, we can make some interesting observations. Observe that if the coefficient of x square is positive, then the transverse axis of the hyperbola lies along the x-axis. Similarly, if the coefficient of y square is positive, then the transverse axis of the hyperbola lies along the y-axis. Note that both the standard equations of a hyperbola contain even powers of x and y. Therefore, a hyperbola with its center at the origin and the transverse axis along either the x or the y-axis is symmetrical about both the coordinate axes. What this means is that if a point px, y lies on the hyperbola, then points minus x, y, x, minus y, and minus x, minus y also lie on the hyperbola. A hyperbola in which semi-transverse axis A is equal to semi-conjugate axis B is called an equilateral hyperbola. The standard equations of a hyperbola also specify certain conditions for the position of its curves. Rearranging the standard equation of a hyperbola with its center at the origin and the transverse axis along the x-axis, we find that the modulus of x upon a is greater than or equal to 1. This implies that for any point on the curve of the hyperbola, the value of the x-coordinate is less than or equal to minus a, or greater than or equal to a. Thus, no point on the curve of a hyperbola with its center at the origin and transverse axis along the x-axis lies between the lines x is equal to minus a and x is equal to a. Similarly, rearranging the standard equation of a hyperbola with its center at the origin and the transverse axis along the y-axis, we find that the modulus of y upon a is greater than or equal to 1. This implies that for any point on the curve of the hyperbola, the value of the y-coordinate is less than or equal to minus a or either greater than or equal to a. Thus, no point on the curve of a hyperbola, with its center at the origin and the transverse axis along the y-axis, lies between the lines y is equal to a and y is equal to minus a. A line segment passing through a focus and perpendicular to the transverse axis, and with its endpoints lying on the curve of a hyperbola, is called its latus rectum. Since a hyperbola has two foci, it has two latus recta. Consider a hyperbola with its center at the origin and the transverse axis along the x-axis and latus recta AB and CD. Let length AF2 be L. If C is the distance of focus F2 from center O, then the coordinates of point A are C, L. Recall the standard equation of a hyperbola with its center at the origin and the transverse axis along the x-axis. Since point A lies on the hyperbola, its coordinates must satisfy the standard equation. Substituting the coordinates of point A in the standard equation of a hyperbola and simplifying, we get L is equal to b square upon A. Since the hyperbola is symmetrical about the x-axis, distance AF2 is equal to distance F2b. Hence, the total distance AB is equal to 2b square upon A. Distance AB is the length of the latus rectum. Thus, the latus rectum of a hyperbola with its semi-transverse axis equal to A and the semi-conjugate axis equal to B is given by 2b square upon A.